valleys and mountains and craters, and it came alive.
Now on Breakthrough.
This activity
This is the
that is
13th magnitude star.
Probing the secrets of the universe
If you don't take the risk and stick your neck out,
and opening new doors into
I
science.
remember growing up in the streets of New York.
You have to wonder whether it's really our world, and you don't really know, but you take the chance.
This program is made possible by the Alfred P. Sloan Foundation to highlight the contributions made by all Americans to progress through science and engineering. Additional funding is provided by the National Science Foundation, supporting education and research in science, mathematics, and technology. And by Intel, through the Intel Foundation, proud to support programs that encourage the entry of people of color into careers in science and technology. Intel, maker of advanced computer chips.
I think I was 7 or 8. I forgot the exact age, but I was there in the Bronx where I grew up, and I met there's a childhood friend of mine who, we'd go out to play several times a week. Well, this one particular time he had a pair of binoculars, borrowed from his father, and he said, "Neil, have you ever looked up with these things?" And quite frankly, the answer was no.
My father brought home some books about space travel. These were books by an author by the name of Willie Ley. And what was amazing to me, and I was probably in first grade, 6 years old, but what was amazing to me was that I found out that space and stars and the sun were places you could go.
I also very much admired detectives. I really liked all the Nancy Drew books, and I thought I might, do something that was kind of intriguing. But that was more for fun. But I always pictured myself as traveling a lot and having a lot of different experiences. I realized that my background was very limited.
slowly but surely I was not encouraged to go into other fields like medicine because my family wasn't rich, like law because I was told I didn't have the gift of gab. And so it was sort of, well, that was what was left, science.
So for the first time, I actually looked up and out with these binoculars, and I saw the moon. It was a first quarter moon, and it was gorgeous. What was most significant for me is that the moon wasn't simply bigger. It was actually better through binoculars than the unaided eye. It had valleys and mountains and craters, and it came alive. It was there. I could reach out and touch it. I thought about it, and if simple binoculars, 7 by 35 binoculars, could do this for the moon, just imagine what those big telescopes could do. From that point on, I just had to think to myself, I want to see too.
The arid foothills of the Andes. Neil Tyson, a member of the research staff at Princeton University's Department of Astrophysics, is returning to Chile.
It's always beautiful to drive up the Elqui Valley. You go through the switchbacks as you get nearer and nearer to the telescope. And so there's a certain drama to that, and a certain romance to that. And as the telescope dome gets closer and closer and closer, there's a little bit of excitement there. I think the most striking moments are when night descends and the anticipation of the observation, it becomes a reality.
It's early May, the beginning of winter here, and the nights are getting long. More importantly, at 30 degrees southern latitude, the giant telescope of Tololo is in the right spot. At this time of year, the center of the Milky Way will pass directly overhead in the middle of the night. For Neil, this means ideal conditions to observe a region of our galaxy that is some 26,000 light years away.
We're about 2/3 of the way out from the disk of the spiral galaxy that we call the Milky Way. And in towards the center, we have the bulge. At the bulge, the region is small enough that doesn't really extend that far above and below the plane of the galaxy. So here we are embedded in the disk. We want to see towards the bulge, and there's a lot of stuff in the way. There's gas clouds, there's dust, there's things that really obscure your view to the galactic bulge. And so you don't have a clear view. A second constraint is that it's a very dense region of stars, so that a single image that you might take of the galactic bulge is just packed. It's just packed with stars. I wanted to go here, and we went west.
Neil gets right to work.
Yeah, so-
Time on a big telescope is precious and tightly rationed, and he has just 3 nights to observe 600 stars he's carefully selected from earlier surveys.
Oh, because this is split between the two, so
Yeah,
there'd be
right.
2 together here.
Those two is those two.
Neil
I just wanted to
Tyson
find
and telescope
some-
operator Manuel Hernandez struggle to locate their
Yeah, I
targets.
couldn't see this one. It was just too dim.
Many are very faint, and even with precise coordinates, almost impossible to spot.
I move a little out.
Yeah. We should be able to find these 2 here. And we should be
There.
about 1 centimeter below. It's the first time the trailblazing part of it that is actually the excitement of doing research. And the first time through the woods can be as slow as molasses. I remember growing up, you know, in the streets of New York, just to get any respect at all. You know, being smart is not in the list of things that get you respect in the street, but being athletic is. When you're a kid, you want to be respected by your friends. You know, you want to be popular. And to be popular, I had to be athletic. And so I was athletic. It was a priority of mine.
But Neil never forgot the image of the moon. Soon he was reading every astronomy book he could find at the local library. On his 11th birthday, assembling his first telescope, observing sunspots in the middle of winter. 2 years later, summer astronomy camp in the Mojave Desert. Neil's photograph of Cygnus, the Northern Cross. His goal was now clearly in view, but getting there wouldn't be easy.
By pursuing an academic path, that seemed to be, at least in society, almost the path of greatest resistance. Primarily because if I tell people I want to do athletics, they say, oh, sure, you know, here's the opportunity, here's the ball, here's the court, here's, you know, come to school, stay late after school, we can train you on that. And it's, the system seemed to be set up to allow me to be an athlete. But when it came time to studying academics, all of a sudden it was, well, I don't know if we can allow that, or I don't know, you, you know, we can't let you have this book more than 2 days, or this is closed to you. And all of a sudden, it was a fight. It was a fight. And I just thought that was astonishing to realize this. And I began to learn that society, when they look at me, they see an athlete. They don't see an astrophysicist. You're much brighter here.
Oh, we have 2 there.
Yeah?
One by one, Neil centers the telescope's optical fibers on his first set of stars.
Oh, is that one?
What is the star number? 36.
36.
Yeah, I think it's right there.
With all 26 fibers in place, he takes an exposure. Then he repeats the process for the next set of stars.
Yeah. Fine.
This is the guy.
For 3 nights, Neil pursues his stars. But time and again, thin layers of clouds block the telescope's view. Neil Tyson and colleague Michael Rich keep adjusting their plan, ready to take advantage of any break in the clouds.
Because we can't see the cluster center, then.
I have only one position.
I looked in the eye, I looked in the D. No, there was nothing there. There was nothing, I was astonished.
When the sky finally clears, it's too late. Neil has observed only a fraction of the stars on his list, but clouds are just one reason astronomy takes time, and he'll be back in Tololo next year to complete his history of our galaxy.
We live in the Milky Way, and it's one of the few galaxies we ever have any hope of understanding in any great detail. And it's a tough task because you're embedded within it. You know, it's like the unborn child trying to figure out what its mother looks like. You're in it, so that's a very difficult task.
Back in Princeton, Neil Tyson catches up with another collaborator, theorist David Spergel. He studies the bulge of the Milky Way using infrared photographs from the COBE satellite.
Is there anything about the structure that you already know from these images, so to help constrain?
And one of the very exciting things that COBE showed us, besides the cosmology results, are the fact that this side of the bulge is brighter than this side. You can
Based
see
on the
it here.
distribution of light seen in the satellite pictures, David Spergel has created computer models of possible star orbits in the bulge.
You have some sample orbits that you've run to
Yeah,
simulate?
just to get a sense of what kind of information we're going to be getting from the spectrum.
Okay, so if you have one I can dig up here?
The data from Chile reveal the actual movement and relative age of individual stars in the same region of the galaxy. Combining Neil's observations with David's models will lead to a richer, more comprehensive account of our galaxy's history.
Okay, so this is obviously a projection into 2 dimensions of what's actually moving in 3 dimensions.
Now, every time it goes from the bottom of the screen to the top of the screen to these orbits, take about 10 million years.
So you tell me if I'd stayed at the telescope for 10 million years, that would have seemed very interesting. Kinematics in the inner galaxy. So if this is the center of the galaxy at 0, 0.
Later that day, Neil takes a break from his stars to go wrestling. At Harvard, Neil was a member of the varsity team. Here in Princeton, he joins the workout just for fun.
Well, I've wrestled ever since high school. Wrestled in high school, college, and graduate school. And even through part of my postdoc, I rolled around with the team here in Princeton. It was a wonderful escape because particularly in college, where if a problem set was getting the better end of my time or of my energies, I would just go wrestle.
There's this episode of a television comedy show that used to come on that had a young man who attended MIT, and at the conclusion of that show, I went to my father as a young 14-year-old naive person and said, well, I want to go to college at MIT. And he didn't say no, and he didn't say it was impossible. He said, we'll see what, I remember his answer is that we'll see what we can do.
I was told that Stanford was a, oh my goodness, you got accepted to Stanford kind of thing, like Stanford was way up here and I was way down there, and that there was certainly ways to fail, and that might be one of them.
My friends were kind of proud that I was going to college and everything. I had very mixed feelings about it because I loved my friends, I loved East LA, I loved the Mexican community, and I felt like I would be leaving it. And I had a lot of problems with that. I got into a lot of trouble in those years, drinking and troublemaking, and my thoughts weren't very clear, but it had a lot to do that, of being torn about leaving your community, sort of leaving the barrio, but you grew up and you loved the barrio.
George Castro, a senior research scientist at IBM, has waited a long time for this moment. It has taken him 5 years to develop his ideas, draw the blueprints, to iron out every detail. For 5 years, George is worried about cost, about delays and setbacks. But finally, the waiting is over and the new machine is here. Now there's just one last question to worry about. Will it work? If it does work, this machine will allow IBM engineers to scrutinize new computer materials in unprecedented detail. Using X-rays to create an image, George's microscope will gently probe test samples down to the scale of single molecules. At least, that's what he's hoping for.
When you're building something new, you fundamentally don't have anything to show for it until it works. And until it works, you haven't proven anything, and there's a chance that it won't work. So you're really sticking your neck out when you're off to build a totally new capability. But on the other hand, if you don't take the risk and stick your neck out, who will build such things?
Overlooking San Francisco Bay near the high-tech world of Silicon Valley are the Lawrence Berkeley Labs. The very building that was home to Ernest Lawrence's first large particle accelerator now houses a brand new machine, which will produce the X-rays George needs to run his microscope. The source of the X-rays, a circular racetrack for electrons called a synchrotron, is located in a heavily shielded tunnel.
The electrons come down a hollow in this tube. This is a hollow thing that has two sections, one where the electrons primarily are directed, and it's connected to another hollow for which we have various pumps and gauges. The electrons will travel nearly the speed of the light down a straight line until they either hit a magnetic field or something else to deflect them.
The electrons make the 200-yard trip around the synchrotron more than 1 million times per second.
Right at this point, X-rays will start to fan out. You'll notice the pipe get wider, and then there are long pipes attached to it such that X-rays can be guided through it and sent to users downstream.
Then the X-ray beam emerges from the tunnel.
Then after that, the next place that you could see the beam is right here. This is the first pair of slits. And if you look right in there, the slits have been covered with a phosphor so you can see the bright reflection.
At the end of the line, the microscope is being assembled for its first test. The new machine may give IBM a competitive edge in the never-ending race to make computer circuits faster, smaller, cheaper. For George Castro, the microscope is an opportunity to crown his 30-year career as a research scientist. A career built on talent and hard work, but also a moment of pure chance.
I'm not totally sure of the reasons why we moved a lot. I think it was because we were very poor and our fortunes went up and down. We always rented and never had control of that property. And sometimes other things would happen. A freeway would come through or an owner decides to sell and we'd have to move.
One of the Castro's many moves changed the course of George's life.
I was in junior high school and we moved out to a rural area, and I was the only Mexican kid in class, and there was an all-white class, and they were all preparing to go to high school the next year, and they were all preparing to take algebra. So I started learning that.
The following year, the Castros moved back to East LA, and George returned to his old school, now with new aspirations.
On coming back, I decided to take algebra, and that completely turn around the nature of the school that I was going to. I went back to the same junior high school, but instead of being in the same classrooms with the Chicano and black students, I now found myself totally in the classes with the Japanese and the Jewish students. And these were now the academic kids, the college-bound kids, because they were taking algebra. And once I got in there, I got tracked along with them as being college-bound material, and then I could do no wrong. So moving out for that semester made a tremendous difference in my life. Otherwise, I would have probably gone on and become an industrial arts major and, majored in wood shop or machine shop, which is what all my other Chicano friends did.
At the Berkeley labs, the microscope is finally all in one piece. George has only a few days on the beam line to run his first set of tests. A couple of graduate students are helping him with the critical alignment of beam and microscope.
We know the beam is coming right through down here. We put a phosphor in here, eyeballed it, and made sure it was coming in here. But we're not exactly sure if that's still hitting right in the center of the chamber where it should be.
To see where it's hitting, George adjusts the beam to allow visible light to reach the microscope. A small alignment problem now is obvious.
No, you're just seeing the white light. See it right on the shield wall?
The shield of the microscope's lens is blocking the path of the beam.
About one revolution. We'll go all the way around.
Yeah. Probably we just these two legs that we raised to begin with.
George moves the microscope ever so slightly.
I think we should just keep going. Is it moving the right way?
And after years of preparation, he's finally going to see the first image. George hopes for a clean, crisp picture of a waffle, a tiny test grid magnified 1,000 times. But the first image comes up blurred and unstable.
I mean, the brightness just changes like mad.
I don't understand this. I've never seen that before.
This cable's acting up.
What looks like a glitch turns into a frustrating and time-consuming puzzle.
We have 3 more days of quality time, and we would like it to fix itself within the hour so that we could use that time. That's the thing with these darn synchrotrons, is that it's not enough to fix it by next week. You just miss all the good time that you have.
Despite the team's efforts, the picture remains a blur. But the next day brings dramatic progress.
No.
The picture on the monitor is still fuzzy, but at least it is stable. Finally, after hours of tweaking, the test grid comes into sharp focus.
Well, you're right on the money now.
The image allows George to gauge his success.
This is a metal grid, and we know the spacing is 25 micron by 25 micron. Human hair would be about a couple of these. These line widths themselves are the order of 6 microns. And some of these smaller defects we see are the order of 1 micron. And the ultimate of this microscope will be an improvement that we should be able to resolve features 1,000 times smaller than this distance.
At the IBM Research Center, George will use these test results to refine his microscope until it reaches its full potential. Even now, after more than 30 years, George Castro still remembers just how difficult it was to find his way to a career in science.
I had never, ever seen any scientist or successful Mexican-American person who was not either a movie star or a businessman. I didn't appreciate that, poverty and culture are 2 different things. and that you can still be part of your community without being poor and living in the poorest neighborhood. So that's where I was confused. I thought I was going to have a new, totally different way of life. I'd have to move away, and I couldn't hang around with the kind of people I grew up with. So that was what was confusing in my mind.
I was the type of child that would go to his parent, his father or mother, with all questions of any time, day or night, about any subject one can imagine. And to me, the remarkable thing as I look back on that experience, though, is how adept my father was at answering my questions. I cannot remember him ever telling me that he didn't know the answer. And that had a very powerful influence on my life because I got the idea that my questions always had answers.
People say that your family relationships, your sibling relationships affects you at least as much as any other factors. And certainly being the oldest of 12 and being kind of a responsible person from birth made me, in part more serious. I had younger brothers and sisters who sort of would defer responsibility because they knew I was there to take it on. So I had that. And, I'd come home, I'd iron lots of shirts, I'd fold lots of baby diapers, I'd help with the cleaning and all that kind of thing. So I really put in my time doing that, which is probably the single reason why I wasn't overly enthusiastic about getting into domestic life right off the bat either, and deferred that for a while.
Robley Hall, 1965. At Stanford, France Cordova majors in English. In her junior year, she spends 3 months doing anthropological field work in a remote village in Mexico. France finds new ties to the Mexican heritage of her father during this period. She writes about her stay in Santo Domingo and compiles a cookbook with favorite recipes from the village. After graduation, she becomes, for one issue, a guest editor of Mademoiselle magazine. I want to be always moving, changing, expanding my sensitivity, she writes in her introduction. The year is 1969.
Forward. 40 feet down, 2.5. Picking up some dust. Straight shadow. 4 forward, drift into the right a little. 30 seconds. Forward, just. Contact light. There seems to be no difficulty in moving around as...
Well, it was during that summer, actually. That was the summer of '69, and that was the time of the moon landing. But about the same time, I'm not sure exactly in what sequence, but it might have been very shortly after that, I was watching late one evening a special on the public broadcasting network on cosmology. And they interviewed a variety of scientists. They had wonderful illustrations and discussions of the different kinds of cosmology. And I just thought that was really thrilling.
Following her growing interest in astronomy, France visits the Palomar Observatory for the first time as a tourist. Later that year, the fledgling writer jumps at an opportunity to become a substitute high school science teacher.
I thought, well, I could probably keep ahead of the students, and so I just accepted. And so I taught for the remainder of that year, and it was just such a great experience to be closer to the sciences and physics that I decided I would start going back to school in that, which was quite a change because as my father put it, he'd already spent all the money for the other education. And so, but I went to a local state college for a year and took background courses in physics and math, and then went over to Caltech and knocked on the door of a person that later turned out to be my advisor and asked him if I could do some work for him.
10 years after watching the moon landing on television, France Cordova receives her PhD from Caltech. She quickly establishes herself in the emerging field of multi-wavelength astronomy. A member of the research staff at Los Alamos, named one of the nation's 100 brightest scientists under 40, department head of astronomy and astrophysics at Penn State. In 1993, she becomes the chief scientist of NASA. Today, she accompanies Administrator Dan Golden to a budget hearing on Capitol Hill. The space agency's budget is under attack in Congress, and the NASA team is expecting a rough meeting.
What specific cuts would you recommend if we're given this DEFCON 13.7 billion target?
We could lose either a space station or we could lose a major science mission. We don't know how to do it without that level of a cut.
What would be the consequences of canceling ACSF or canceling Cassini?
First, on ACSF, to achieve the science that ACSF will achieve, which is really the high angular resolution in the X-ray wavelength band, cannot be done, has to be done from space.
No matter how well you prepare, it's really hard to anticipate what the questions will be. So in that sense, it's always kind of a terrifying experience.
First, let me start with the cost, though, and then I'll talk a little bit about the science.
But also, if only one could survive, what would you recommend?
That's a question that is not to be made by us. I mean, that's a question that, if it comes down to that, has to go out to the scientific community to make those kinds of priorities, those kinds of choices.
Well, but I am asking you this. I am asking Dr. Golden this, and I am asking you this, Dr. Cordova. Otherwise, why have a hearing?
Either one is painful. If they had to be canceled, we would pick one and cancel it.
It's unfortunate that it has to be played out in such a short, intense way. And it's not just NASA's problem. If it were just NASA's problem, we would meet behind a closed door and we would solve that problem. But it's really the country's problem.
Despite a heavy schedule at NASA, France still manages to pursue her research. This spring, she is trying to find a new piece to a cosmic puzzle. Sometimes, when a giant star suddenly collapses and blasts itself apart, what's left behind is a super hot core, very dense and very small, perhaps 20 kilometers in diameter, spinning rapidly and sweeping space with a bright beacon of gamma rays or X-rays, a pulsar. Over time, pulsars cool off and grow dimmer. Old pulsars have never been observed in the visible and ultraviolet spectrum. With the help of the Hubble Space Telescope, France is trying to do just that, catch the visible light of a star that died thousands and thousands of years ago. At the Space Telescope Science Institute in Baltimore, France is eager to get a first look at her Hubble pictures. They will show a very small slice of the sky, the exact location where a pulsar has been spotted in the X-ray band. But there's no way of knowing whether France's pictures, taken in visible and ultraviolet light, will show the pulsar at all.
Wow, there's a lot of things there. Yeah. Goodness. There's a lot of objects here. Oh, it looks like there was a comet or something that went through.
I think it's a bright star.
Just a bright star. Oh.
I'm going to redisplay it with the compass.
Oh, maybe this is the 13th magnitude star. Yeah.
There are several stars in France's picture. It's not clear which one, if any, is the pulsar.
Boy, we're going to have to get good positions on, on a lot of these, as you can see. But I'd say that there's at least a couple stars that are, well, a few of them that are close enough to the center.
Switching back and forth between two filters, France Cordova and astronomer Laura Danley compare the stars closest to the center, the expected position of the pulsar.
This one is much brighter in this picture than this one. So this is just a bluer object.
Yeah. Almost the same brightness in each of both the broadband and the...
That's right. That's right. I mean, we can definitely
France knows that the bluest star in her picture is most likely to be the pulsar.
But I guess a big question is whether the object that's the closest to it, which is quite a bit brighter, is also blue or not. That's what I really would like to know.
So are you happy with it?
Oh, yes.
Looks gorgeous.
Very excited. So,
you can't find out. Tell the difference.
I think it's the faint one. Do you want to bet on it?
We should. I think it's probably the faint one too. But
A thorough analysis confirms their hunch. France has indeed captured visible and ultraviolet radiation from a long dead star.
what we wanted to do was to look at the whole spectrum of a pulsar, because the X-ray observations just gives you the tail of that spectrum, the high energy tail, and it's trying to understand whether you're looking at the right spectrum is equivalent to a blind man or a number of them all feeling an elephant, one the trunk and one the tail and one a leg, and then inferring what the shape of the elephant is. That you can't do it unless you have the whole elephant or the whole spectrum.
Even in her free time, France finds new challenges, running the Boston Marathon in 1977. A few years later, she meets her husband-to-be, Chris Foster, in a rock climbing class. This summer, the couple is giving their kids a first taste of the sport.
Let's grab. You ready? Now, put your feet against the rock.
No, not yet.
Go right up that crack right there, Steve. Push straight down with that hand. There you go. Keep going. Keep pushing. Oh, yeah, that's it, Steve. He was getting up there pretty high.
So can I come down?
Sure.
Put your weight up on here.
Lift
up on there. Yeah, that's right. You're good at holding your body out. So
The crack is to your left.
that's right.
Over here? Yeah, right with your hand where your thumb is being cracked.
I can't do this.
Oh, that's
What
great.
did we say was supposed to be? I don't know. What do you want it to be?
That's great,
Mine too.
Annie.
Okay.
Put your foot in there. See? Right there. Okay. Do you want to come along? This is the crack that Stevie did. Do you want to do that one instead?
Take me down.
Just hold on to the rope, Aunt.
You've been up higher than that when you've been climbing the rope.
Sometimes in your life, you can identify a few moments when you say, there's something about this activity that is just you. And that's how rock climbing was for me. Every placement is like a whole intellectual problem, and you're not resolving any of your personal problems or any of your mathematics problems or anything at that point. You are just trying to figure out this move. And you're trying to do it in such a way that conserves your strength and your balance, because you know that if you don't, then you're not going to make it all the way up.
Big swing here. The sun now, down here. Okay, I got you. Attention. There you go. All right. Just a little itty bitty like that.
Okay, I'm at the anchor, Chris.
After the initial sort of interest in space and space travel, I started building up images in my head about what it would be like to be in a spaceship. What is it like to travel between planets? What do the planets look like when you're in a rocket looking back at the planets? Through those exercises, I understood that the imagination was a very powerful thing that one could use to sort of build worlds within one's head. At some point, I realized that what we were doing in mathematics in school was very similar, that we were given these rules, the simplest being 1 + 1 = 2, but we were being given these rules and then asked to find consequences of the rules.
Yaroslavsky Station in Moscow. Jim Gates, professor at the University of Maryland and an internationally known theoretical physicist, is on his way to Siberia. He is making the trip to meet scientists from the university in Tomsk, with whom he has maintained a long-distance dialogue for many years. Hoping to get a good look at Russia, Jim is taking the train. trip from Moscow to Tomsk will take almost 3 days.
When I was in high school in the 11th grade, I actually took my first physics course. And immediately upon taking the course, I recognized that physics was doing something very strange that I had not known was possible. In physics, the language of physics is mathematics. And for me, by definition, that was the world of the imagination. That was something inside of me. On the other hand, when we do physics, we write equations that describe things that take place in the world around us. So there was this very simple experiment where we rolled a ball down an inclined plane and had a stopwatch to measure how long it takes for the ball to reach certain distances. And you can show very simply that the distance the ball travels goes as the square of the time that you wait. And this was, to me, a totally shocking revelation, because here I saw the real world, the external world, being combined with my world of imagination, and I recognized immediately that that's something I wanted to do. A large part of doing theoretical physics is like swimming in a sea of information. And it comes at you from many, many sources, some external, some internal, friends, reading the literature. And all of this information sort of goes into your blender, whatever your own individual device in your mind for putting facts together, and comes out in a slightly different way. And so having produced something slightly new, you then feed that information back into the community, and someone else picks up on that new strand, and you can't tell where this process leads.
In recent years, this process has taken Jim Gates and his colleagues to an uncertain place. They belong to a prominent group of theorists scattered around the globe who are trying to make sense of a puzzling new theory, superstrings. A theory that finally manages to unify gravity and the other fundamental forces of nature in a coherent mathematical description. This is the problem Einstein never solved, the problem that has plagued theoretical physics for more than half a century. But Jim and his colleagues are not celebrating yet. They don't understand why superstrings succeed where everything before them failed. Early in his career, Einstein was struck by an idea. If a person falls freely, he will not feel his own weight. Einstein later called this the happiest thought of his life. Though hardly a discovery, the idea propelled Einstein towards a new description of gravity. Einstein soon found another image to illustrate the same idea. Imagine a man in an elevator. Suppose the elevator is not moving, but standing still. Naturally, the man will feel the pull of gravity, the familiar feeling of his body's weight. What if, Einstein asked, what if we move the elevator to outer space, far from Earth's gravitational field? Our man floats, weightless, unless the elevator accelerates and keeps accelerating. Then the force of acceleration acts just like gravity, and our man in the elevator feels the same downward pull.
Einstein gave us a beautiful analogy that we can directly take from prosaic language and produce mathematics that then is quite remarkable in its power and depth, but also allows us to capture the essence of what he did in his theory of general relativity. This principle, which Einstein called the general principle of equivalence, is not something that we understand for string theory. And because of that, the theory is in some sense evolving backwards. We have the mathematics, but we don't understand the physical essence that produces this mathematics. Until that happens, we will be somewhat limited in our understanding of string theory. And unfortunately, it's been 10 years now with an army of the world's best physicists looking for this man in the elevator. We still haven't found him. I had an idea last night, just before I went to sleep, about a new possibility that had not been noticed before. So I set up some calculations, first of all, early this morning, and now it's crunch time. I'm trying to find out whether this possibility actually exists or not. These are the times when it's very difficult because it's very frustrating to be very close to an answer and not be able to push it all the way through to the end.
By the time the train reaches Tomsk, Jim has not finished the mathematical definition of his new type of superstring. He'll try to find time during his week here to complete the calculations. Karl Marx Street, 14. Jim's conference is taking place in an old party school that now houses a conservatory of music. The first day features presentations by Joseph Buchbinder, a leading theoretician from Tomsk, and Bert Everett, a physics professor from the University of Pennsylvania.
You see that as time goes on, this thing goes to zero because of the fact that epsilon.
By the end of the session, there is plenty to talk about.
New equation of such order,
but I don't.
Such order, and this equation are not regular. Is not regular.
Yeah, but I don't think that that's correct. I believe that you can make a redefinition of variables that does not have an extra constraint. In fact, I know you can. Okay, and I.
Вот по-русски вы хотите ему сказать, что это уравнение несовместно.
I'll study this paper when I get back, and if I have any more comments, I'll send via email to you. Because electronic mail seems to be working quite good between Tomsk and here.
The scalar field psi is defined as a log of a curvature. The curvature has derivatives in it.
Work at a given level in the string theory, and then you want things to be consistent from that level down, and you don't worry about contributions up. And that, in some sense, this is what this is begging to.
I think this is saying that we're going to the massive level. Yeah. And that Gauss-Bonnet is massless, but the minute you go to the massive level, you have to worry about these things.
Jim's presentation is scheduled for the next day. In his hotel room, he prepares the transparencies that will accompany his talk.
Just prior to departing the U.S., had been able to prove that there are more strings of a particular type than we had imagined. And there's this construction known as the n=4 string, and up until the work that I just completed, we'd always thought this was a unique mathematical construction. But now, in fact, I have an explicit proof that there are at least 3 of these objects.
Jim is eager to share his new results with his colleagues in Tomsk.
If you differentiate S and P, you find out that these 2 equations are satisfied. Now, if you eliminate W between these 2 equations, you in fact rederive the differential equation that I first showed you was the definition of a twisted chiral superfield. This new sort of potential world that we're creating with this idea of supersymmetry is very exciting. It has some beautiful mathematics associated with it. But in the end, you have to wonder whether it's really our world. And you don't really know, but you take the chance. If we start off with a complex superfield, then that means that there are 2 spin-zero states as its leading components. And that's part of the risk of being a theorist, is that you have to take the chance. The only place you see it is when you impose the constraints that define the string. And so you very much like a detective, you follow your sense of a lead. I'm sure that this will kick off something here in Tomsk. They have a very good group of students that they work with. And now that I've sort of given this information, I'm going to wait to see what the return information is.
The last conclusions were very, very interesting for me. I think it can be base for new researches in this field.
He also mentioned the fact that there's a so-called mirror symmetry in the Calabi-Yau compactifications of strings, and that he could understand that from the point of view of mapping back and forth between twisted and untwisted things, which I thought was just absolutely delightful and brand new to me.
By the end of his stay in Tomsk, Jim Gates has worked out the mathematical proof for the 4th in his quartet of superstrings.
Is equal to I times gamma superscript C alpha beta subscripts times partial derivative with respect to C R tilde subscript I superscript J, all multiplied by Kronecker delta I times J. From this
With care and satisfaction, he copies the equations into his notebook. He hopes that his classification scheme, like a periodic table of elements, will serve as a map to the strange new world of superstrings.
As a research scientist, one makes one's presence known by contributing to the research literature, writing research papers, submitting them for publication in scientific journals. And then once they go to the journals, it's a little bit like putting a message in a bottle and casting it into the sea. You have no idea where that bottle will wash up. You don't know whose shore it will be and what individual will walk along and pick up the bottle and read the message.
It's been a difficult path. Difficult because there's this sort of extra social tax I have to pay just to do what I want to do. But I call it a tax, not a burden, because if I viewed it as a burden, that would, I don't know if I'd survive it. But a tax, just pay the tax and just keep going.
Fundamentally, you have doubts all your life whether you should even be here. When you think of the luck, you think it's not all merit. But after you're older, you realize that, breaks come every day to somebody, and it's what you make out of them.
Most of us can't figure out if we're really shy or we're really not. And I always would describe myself as being, more shy. But when I look at it, I did all the things that were not very shy.
And at a certain point, you realize, when you look at very great science, you realize that you're a member of the same species as a person who made the discovery. And therefore, it's your common birthright, just as it is anyone else's. And that's sort of a great feeling. The only thing that I know that's better than that is when you can actually start to contribute that new knowledge. And for research scientists, that's the goal of one's career, to in fact reach the stage where you're putting new stuff into the system so that later young people will be able to come along and say, gee, that funny thing was first discovered by. And that's a pretty good feeling.
To learn more about Breakthrough, Visit us on the PBS homepage at the address on your screen. To learn more about local programs and resources for students interested in science, please call 1-800-BIG-BREAK or write to this address.
Breakthrough is made possible by the Alfred P. Sloan Foundation to highlight the contributions made by all Americans to progress through science and engineering. Additional funding is provided by the National Science Foundation, supporting education and research in science, mathematics, and technology. And by Intel, through the Intel Foundation, proud to support programs that encourage the entry of people of color into careers in science and technology. Intel, maker of advanced computer chips.
This is PBS.
Video cassettes of this program may be purchased for educational use only by calling toll-free 1-800-328-PBS1. Home video sales are not available through this offer.